Okay, welcome back, everyone. We're talking about the last little bit on free boundary value problems. And then I'm going to take you through at least what I understand of a math finance application that involves asset pricing, involving what's known as the Black-Scholes equation. So that's the list. I had actually thought that the Black-Scholes problem was a free boundary value problem, but in fact it isn't. So anyway, that's why I had put it in this section. It's basically just another parabolic problem, a heat equation type problem that we'll consider with some features that make it interesting to look at in this class. Okay, so let's wrap up this discussion of free boundary value problems. We were discussing the oxygen depletion problem, and I'll run you through where we were there and add a couple of comments after that. Okay, we'll let other Brian take over with his tablet. So this is in the okay. Well, my computer just did a little bit of a screen blank there. That's a little alarming. So we were looking at the oxygen depletion problem. It's a scaled model of, you have an oxygen source here at x equals 0. It's one spatial dimension problem. So this is the I put the minus sign, so F, positive F means a flow in. So this is the flux of oxygen into the tissue. X, this is tissue depth. Away from this capillary or whatever that is. And there will be a free boundary. So a free, or if you reserve a free for a steady state, this is a moving boundary. I don't, my free boundaries can move, but that's something that changes in the literature depending on where you're looking. And then past here, there's no oxygen left because in here, it is diffusing away from this input, but also being consumed. Now, this is, except for the free boundary, this is a very simple reaction diffusion equation, where the reaction term is the simplest one you can imagine. It's just a constant. We're going to look at other reaction diffusion scalar problems and then vector problems. We'll look at traveling waves, and there's an interesting phenomenon that leads to pattern formation, which we'll look at in the context of vector reaction diffusion systems as well. That'll be the last topics of the course. Okay, and so you'll notice on the assignment that was posted over the weekend, due next week, that there are some Analytic questions. The only ones I could ask about free boundary value problems are steady states in pretty simple situations. And that's where we ended last time on this problem. We took f to be 1, and we found the steady state to be u of x is 1/2 x minus 1 squared. And so the s at 0 was 1, right? Oh, I forgot to remind you the free boundary conditions. At the free boundary, we've got u is equal to 0. That's a boundary that's enough to solve this problem if you knew what s of t was, right? Because you got a boundary condition on one side and a boundary condition on the other side. But you need other information to tell you about the boundary motion. And that was, this is true also at the free boundary. Now, can you say one determines the PDE and one determines the free boundary? Okay, not really. You got two conditions and two things you need to close the specification of this problem. And these are the two things that you get at the free boundary. Okay, so let me do a little bit of math for you. Okay, so this, remember, this was different from the Stefan problem that we started with, where we had an explicit expression for the velocity of the interface. You know, v was that jump in normal derivatives at the moving boundary. Here, there is no expression for the velocity, right? So this is what's known as an implicit free boundary problem. There's no interface velocity expression. We just have an extra condition at the boundary, which implicitly tells us how the boundary is going to move. So implicit. There's a little bit of a trick you can do in this particular problem. It's not clear to me how general this is, but I thought this was interesting enough to show you. Let's consider the oxygen depletion solution u of x and t. So I'm saying I've got one. I've got a solution of that problem. It's a well-posed problem. And now I'm going to look at v of x of t, which is going to be the time derivative of that solution. And so let's look at the problem that this solves. Okay, well, let's have a look. I'm going to take f of t to just be a constant. So if I take the time derivative of this thing, right, I'll get Vx is equal to 0. If I take the time derivative of this equation, I'm going to get Vt is Vxx. So V satisfies just the heat equation. Let's have a look at what happens at the free boundary. I know that here both u and ux are equal to 0. Well, let's write that out in a little bit more detail. Okay. Do I want to do that now? Yeah, okay, I'll come back to it. So I know that u of s of t and t is equal to 0 for every t. So now I'm going to take the derivative of that with respect to t. And I get two terms, right? I get s dot ux of s of t and t plus ut at s of t and t is equal to 0. Okay, so let's have a look at that. This is v at s of t and t, and this is 0, right? Right, because everywhere I look on the free boundary, that's 0. So this tells me that I've got v is equal to 0 on the free boundary. Okay, not really a surprise. When I look at this one being 0 at s of t and t, I'll get something interesting. Let me come back to this picture and tell you about initial conditions. Well, I want the time derivative of v of u at time equals 0. Well, all I've got is some initial conditions for u. How do I get the time derivative? Well, there I have to use the equation. Right, at time equals 0, this equation is still going to be solved. And so I know that the initial data for v has to be u naught double prime minus 1. Okay. The other thing, what do I want? What order do I want to do this in? Okay, there's a thing I have to add to the derivation below, and I was just not quite sure when the best place to do it is. So let me start, and then we'll look and see when the best place to do it is. So I started with this, and I want to get the other expression for the free boundary, the other free boundary condition in terms of this problem for v. Right, so let's do the same thing we did up above. Let's take the time derivative. Okay, and let me change my view option, because I realize now that I don't have my Slack channel thing up. It doesn't look like I've missed any questions. Hey, it's a small group. Don't be shy if you've got questions. So I'm going to take the time derivative of this. I'm going to get s dot uxx. This is on the free boundary. Plus utx s of t and t is equal to 0. This is the thing I'm interested in, right? Because this is the Vx on the free boundary. I'm trying to convert my problem that was for u, which was a free boundary value problem, into a free boundary value problem for v, which is the time derivative of u. And here's where I need something, okay? And here is where I look at the original equation. And I go, if u is 0 and it's x derivative is 0 everywhere on the free boundary. That's what got us to this v is equal to 0 on the free boundary. But remember, v okay. v is equal to ut, which is equal to uxx minus 1. So if v is equal to 0 on the free boundary, then there's a higher order compatibility condition which says that uxx has to equal 1 on the free boundary. Right, so that means this thing here is equal to 1, right? Okay, there's a question coming in. Are we choosing to ignore that the x derivative is 0 on the free boundary? No, I am. I'm looking at that now. Okay, so maybe that was a question that came in before and I just missed it. But here I am assuming that it's 0 on the boundary and seeing what that tells me in terms of v. Okay, so if you look at this thing now, you get that s dot is minus vx, right? And now let me write out the whole problem now for v. I've got v 0. I've got initial conditions for v using the derivatives of the initial conditions for u. I've got vx is equal to 0 here. I've got vt is vxx here. And I've got a free boundary value problem here, which I've converted entirely in terms of v. I've got the two conditions, v is 0 and s dot is minus vx. So not in terms of the original variable u, but in terms of v, now I've got an explicit free boundary value problem. In fact, it's like the problem 1 from the Stefan lectures. It's the one-sided Stefan problem that we considered before, where the ice was all at 0 temperature, exactly 0. And we were looking at, well, melting or freezing into that mix. Okay. So this is one of those games in terms of the work we can do to reformulate a problem, either to make it more tractable to mathematical analysis or computational techniques. Okay, so you could solve for v of t with your Stefan problem code, and then recover u of t with, well, v is just the time integral of u, so you could get u by integrating v. Now I'm going to say this is mathematically interesting. But I'll say not a good computational formulation. I'll say in general. And I'll show you why with some pictures. Basically, I don't like this formulation because it does not recognize changes in topology of the U bigger than or equal to 0 set. Bigger than 0. Okay, so let me draw you some pictures. Let's look at the problem for U. Right, and I'm going to give it initial conditions that look okay. I'm going to have Ux is equal to 0. So I've shut off providing oxygen to this problem, right? But I'm going to say the oxygen profile initially looked something like this, right? So I had I'm going to put with what's a good color? Blue dots. I'll put blue dots for where there's a free boundary condition. Okay, so now I'm going to look as time goes on. Okay, so I'm going to draw another picture in time, and you notice, hey, I've got this pretty flat region. Remember, it's ut is uxx minus 1. So anywhere where this is concave up, it's trying to raise up the temperature, right? That's just saying, hey, there's temperatures nearby that are warmer, right? I should heat myself up. And when it's convex, right, then this is a negative term, right? Here it says this bump should go down faster. But overall, I'm still reducing the solution sort of uniformly, right? Not in temperature, in oxygen concentration. So in this flat bit, right, where this term uxx is not very big, I'm just going to basically move downwards. Now, of course, I'm going to have the influence from these bumps coming in, so there's some sort of competition. But I'm going to say that later on, the solution should look like this. Right, and I'm going to have introduced some new free boundary value points. Right, this is what the solution should do. Right, but I need a method that can recognize when the solution goes 0. Right, so that I know where to put in these extra points. This is where a capturing method is gonna shine. Right, and if I look at this equation for V, right, I don't know, right? I don't know, solving that equation, when U is going to go 0 and where I need to put in these new boundary points. And remember, this is something I mentioned before. These boundary points affect the dynamics, right? So it's not like you can compute V and then integrate U and then see some places where U is negative and then just cut it off. No, that does not give the same solution as cutting it off when it is 0 and putting in the free boundary conditions and adjusting how the time dependence of the solution happens, including the effects of the free boundary. An interesting game, right, where you can see the connection between the two types of free boundary problems we've looked at, but not so useful in terms of the general computational problem. Okay, so I've got a little thing here that says that these problems can be posed in higher dimensions. I think I showed you this for the Stefan problem, but let me do it again anyway. So problems in higher dimensions. Right, I'm going to have the Stefan problem. I'll have my water and my ice. I'll have my heat equation over here. right? This is something which we've labeled the Laplacian of U. There's alternate notation for that. Is it only in the implicit case where you may get more free boundaries appearing? No. You can also cook things up so that you get free boundaries in other problems. And remember, we've sort of talked a little bit about sort of the relationship of the formulations we're coming up with in this class to computational implementations. And once you know that there's going to be topological changes in the solution, right? That's where you get like new places where there's interfaces. That's where you really want to think about a capturing technique so that the grid will just kind of automatically detect where there should be some new change in solution type and adjust. Okay, here in this problem, then we had the increased thermal conductivity in the ice. And then on the free boundary, right? Here's where you think this is the explicit one, right? Right. You need three conditions, right? One for the elliptic or the parabolic problem on one side, one for the parabolic problem on the other side, and then one for the free boundary motion. And so here you had a U plus and minus is equal to 0, right? That's two conditions, right? And then you had the explicit normal velocity, which is the jump in the normal derivatives, right? Remember, this is du dn on the positive side minus du dn on the negative side. And you have to be careful of signs, right? Because you can change the sign of this by changing the ice and the water sides. And you can also change the sign if you point the normal vector in the opposite way. And so, yeah, make sure you get your signs right. Or as it turns out, you get an ill-posed problem if you get the wrong sign. Okay, so that was the Stefan problem. What about the oxygen depletion problem? Okay, I'm going to do an exterior problem. So this is a solid, so I'm not solving anything in there, right? That's the capillary that's providing the oxygen. So what I'm going to say is the normal derivative, that's the flux into the domain, will be F of S, right? Where S is now the parameter of this boundary curve. Right, so I'm not solving anything in here, right? This is just something that's supplying some flux of oxygen. And the free boundary then will be something that looks like this, right? And in here, I'm going to solve for oh, the notes forgot the -1. That's really important, right? You're depleting the oxygen. I'm going to have U bigger than or equal to 0 in this region. And on the free boundary, I'm going to have U and its normal derivative equal to 0. And there's a problem like that in radial geometry. So it's not a higher dimensional problem, really. It's just a 1D problem in the radius in the assignment number 8. Okay, so this wraps up our discussion of free boundary value problems. And just to give you some chance to kind of understand them a little bit better, like I say, on the assignment, there are some questions about finding free boundaries, but it's all steady state case, because that's a situation where you can make some analytic progress. And the time-dependent ones really come down to a computational question. Any questions on that before we go on to the next topic? Okay. So the next topic is the Black Shoals equations from Math Finance. Okay, and I have to have a caveat. I'm actually pretty, expert in everything we've talked about so far in the class, and everything we'll talk on after this in the class. But I'm not really an expert on this topic. Okay, and so I have some gaps in the exactly how the equations are derived, and in some of the financial things around them. So finance, that's not my thing. I like science applications. Money is boring. And I'm also not an expert in stochastic processes, which is a part of the derivation. So I'll sort of try my best to take you through what I've learned in the last few days, and we get to a PDE, at the end, which is well accepted in the community, and so then we can look at the PDE and talk about that, and then I can sort of have some expertise again at that point. Okay, so let me take you through the basic idea here. Many people with the training that you have, I'll say your quants, right? Your quantitative analysis, end up working in math finance. So I thought it was worthwhile at least trying to give you a taste of how some of this game goes. So these equations, they're used to price stock options. What is a stock option, you ask? Okay, well, I'll do my best to explain that to you. There's going to be a stock price. And this is modeled as a stochastic process. Any of you out there taken Math 303? There's only a few of you out there, not the whole class. Okay, no Math 303ers. Maybe I should just ask if anyone is actually awake out there. Oh no, I got a question. I know at least Maricela and one student are awake. Okay, that's good enough for me. Let's talk about this stock price. So it's modeled with geometric growth. So there's a term in the stochastic model which allows for a growth that should be exponential growth, right, over time. And here's one of the things where it comes to the model is that coefficient does not enter into the pricing model later on. And there's an economic argument for why that doesn't happen, that involves some hedging thing. And that's one of the things I don't understand. But it's going to have geometric growth and geometric Brownian motion. So there's going to be some random fluctuations to the stock price. And the random fluctuations, have a normal distribution over a fixed time width, whose let me get this right. Whose variance grows with time. And by geometric, it means the larger the stock price, the larger that variation is as well. Okay, so it's really a Brownian motion based on the fraction of on the stock price. Okay, so now I'm going to draw you a sample stock with some random aspect to it. And I'm going to be concerned with options that you buy at time 0 and you can exercise at time t. These are European options where you just buy the rights to take some action at some fixed later time, which is the big T here. So I'm going to say, here's my stock price at time 0. I know what that is. And then I know that it's going to, have these kind of oscillate. It'll grow, right? Maybe over time, right? In some random way, fluctuate around that. Okay, so this is S of t. Of course, sitting at time 0, I don't know how it's actually going to go, right? Because it's got some random aspect to it, right? Maybe these oscillations will in general make it go down, even if the overall rate is supposed to be positive. So a stock option. Okay, and I'm going to describe the easier ones, the European ones. Gives the right, but not the obligation, to buy or sell shares at the strike price, K, at time big T. Okay, and there's 2 types, right? One is the buying and one is the selling. So a call option, these are the ones that we'll pursue in a little bit more detail later on in the lecture. So a call option buyer can buy shares at the strike price at time t, right? That's the exercise time. And a put option buyer can sell shares at the strike price at time t. So let's suppose that you had bought an option with a strike price K that was here, right? Well, you would be happy, right? Because the price of the stock is actually higher than that, right? So you can buy at this price, right? At this price K, and sell it for more money, right? And if there had been a random trajectory that ended up down here, well, then your option would be worth nothing, right? You don't have to buy them at that price and take a loss. So you have no value in those things. Okay, and just to say that if you're the seller, must execute the option if the buyer requests it. Well, and clearly, if we're talking about these call options, right, you're only going to, if you are the buyer, you're only going to, execute the option if the stock price is above the strike price at time t. Okay, and if you're wondering what these things are used for, right, they're speculation tools, right, or hedging, right? If you looked at this and went, right, I can make quite a lot of money if this option was not very expensive, right? And you would think, well, it's not that likely, maybe that the stock price will go up that much in time t. So the option you bought cheaply, but you make quite a bit of money, as opposed to buying the stock and letting it go up, right? You earn something, but the multiplier on your investment is potentially much bigger with these options. What's the hedging part? Let's say you are a company, you don't have the money to buy the stock now, right? But you're arranging to have the funds to buy the stock later, and you need to have a specific amount of that stock to, make some merger work at this time t. And so this is just a way to pay a little bit of money and guarantee that you can execute the plans that you want to make in the future. So speculation and hedging. Look at me talking like a math finance guy, which I am so not. Okay, so let's talk about what the PDE is going to be in. Okay, so let's get that nailed down, right? It's always good to know what you want to know, right? So there's going to be an unknown U coming up, right? Because it's going to be a PDE. I like U for PDEs. So here's what you want to know. You want to know U as a function of S and T, right? And so what is this U? This is the expected value over all random paths of the value of the option if, I'll say, for the given stock price that comes from the random path that takes you there and gets you there at time t. So now you know that there's some sort of complicated probability arguments that come up. And again, I'm not an expert in that. So I'm going to hand wave and get to that. So, okay, why do you want to know this? Well, if you are the option seller, you want to know what you should price the option at, right? Because you know what the stock price is at time 0, right? You know, well, okay, you know this, right? And so you want to look at time 0 and figure out how much this is worth. So this is so that you can value the option competitively, right? If you don't know this value, and you sell it too cheaply, well, you could lose money, right? And if you sell it with a too high a price, someone else is going to be able to work out that they could sell it cheaper, and you won't be able to make the sale. Now the buyer, you've bought one, right? The buyer wants to know you at S of t and t for later times. Right, because you can't execute the option until time t with these European options, right? But you can sell it, right? It's a product, right? So you can sell it in these intermediate times, right? And at that time, you will know what the stock price is, so you'll know what its value is at that time, right? So this is, you want to know this in case they want to sell the option before the execution time. Right? Okay, so let's write down what we know. So we know information. Well, I know the value at the final time. Right? I know if I have a call option, it's only worth something if the stock price is higher than the strike price, and I make that difference is the amount it's worth. Right, and the put option, which you make if you think that the stock could go down, if you were speculating, just the opposite. And so let's only consider call options from now on. Right. I'm going to start working on boundary conditions now. Okay. This is going to end up being an initial condition for parabolic PDE. So a heat equation type problem. If the stock price is 0, okay, Dominic, yeah, we're expecting good things, or I don't know, we're hedging. This is all stuff I don't actually understand. Okay, so this one's pretty easy, right? If the stock price is 0, then the company went bankrupt, right? So if you're hoping to make money by having the stock price above the strike price K, that's never going to happen, right? Right. Remember, in the model, it's geometric growth and geometric Brownian motion. So all of those time derivatives of the stock price are proportional to the stock price. So if it's 0, okay, you're stuck at 0, right? Okay, so once you get to 0, then you know that the value obeys nothing, or the value is nothing. Okay, so now I'm going to write down the PDE. Black Shoals sounds like some sort of spy organization, doesn't it? Okay, but it's two last names. I think they won the Nobel Prize in economics for this. Okay, so remember, I've got U as a function of S and T, right? Right. So S is playing the role of a spatial variable in this problem, right? So this is the variance of the geometric Brownian motion. Right. And then I've got R times S US. So this is like a hyperbolic term. This is like a one-way wave equation term, but with a wave speed. Minus R times U is equal to 0. What's this R? This is the risk-free investment rate. So that's if you just took the value of your asset and you put it in the bank, you know, at, I don't know, what interest rates do the banks pay now, right? But Canadian banks will say have no risk, you know, but that's a very small amount. Okay, so let's have a look at this. Oh, right. Let me admit the things I don't understand. Okay, so this one I sort of get, right? Right. This is something where if your value does not depend on the stock price, right? Right, then USS is 0, and that means the variance, right? Right, because the variance is doing the oscillations on the stock price, won't change the value, right? Okay, so this is something that's sort of plausible in that sense. This risk-free stuff, I'm not quite sure I understand. I go back and forth thinking I have the sign wrong on some of these terms. So there's an economic explanation for those terms, which I'm not quite sure about. And again, there's a kind of a fascinating thing that the expected growth rate of the stock, right, doesn't enter into this at all either. And again, there's an economic argument for that, which some of you may understand better than I do, and it wouldn't be too hard. But now let me go to some discussion where I can start with this equation and say something meaningful. First of all, let's write it a little bit differently. Let me just take all these terms and put them on the other side. This is how we typically answer it. Oh, you may not have an answer, but is risk-free investment rate like the risk premium or certainty equivalent? I don't think so. Okay, I think this is actually just the rate at which you know, investment can grow in a risk-free way, right? This is a value of something with risk, because this is an expected value, not a certain value. So this is, again, this is just the interest rate that you put in, you would get on return on investment in a safe investment, whatever the going rate for that is these days. You know, U.S. Treasury bonds. Well, okay, I don't know how risk-free those are, but that's outside of Math 400. All right, I'm going to say Canadian banks, right? But whatever interest rate they would give you. I'm sorry, I don't have a better answer for you. Let me take these things and put them over on the other side. We'll look at them individually. Minus So if I look at them individually, well, is anyone worried about this term? Worried, anyone? I'm super worried looking at that term. Super, super concerned, right? I don't know what a Cauchy-Euler equation is. Let's just pretend I was looking at UT is minus USS. Would anyone be worried about that equation? Isn't that ill-posed? Right, and this is just some sort of version of that with some positive, coefficients that aren't one, right? Okay, well, here's the trick, right? You'll see how that gets fixed later on, right? Because what we're going to do is we're going to solve this problem backwards in time. So it's ill-posed going for increasing time, but it's well-posed for decreasing time. Because basically the time derivative just changes sign and you get the heat equation, right? Okay, so remember, we've got these are really going to end up being initial conditions, which we're going to solve backwards to time zero, okay? So that's an interesting thing. Don't try and solve this forwards in time from capital T. That won't work. Oh, how did we know that this equation was ill-posed? This is the classic, this is the first ill-posed problem we looked at, right? This was the sine series with exponentially growing terms, and the size of the exponential growth was unbounded, right? Right? Okay, you can look back through the notes on that. I'm also going to discuss well and ill-posedness a little bit more coming up in the remaining topic, because it seems like an important idea that not all the students have gotten yet. This is some sort of convective term, right? And this is just some exponential growth. Okay, and again, I'm not exactly sure about the signs of these things, but I think this has something to do with if your asset has some value, of course, you could always just sell it and put it in the risk-free investment and get this growth, right? So that's always an option. What I don't understand is why there is not an if statement in there then somewhere, okay? So again, some financial details of the model that I'm not an expert enough to help you with. But let's look at this thing and go, well, we can do some Math400 techniques on this thing now, right? So I can do some scaling. I can always scale S to be a little s times K, right? And this makes the strike price to be K is equal to 1. Or I'll say little s is equal to 1 is now the strike price. All right, and if you notice, if I put this substitution in everywhere there's an S, in fact, I don't change the equation. Right, in fact, the scaling K falls out of this thing. And that's really a consequence that these terms are geometric, right? So if I scale the stock price, right, and these random and definite terms are scaled to the size of the stock, right, then it's all a fractional argument that works out, okay? So maybe you didn't understand that comment, but certainly you can do this change of variables and see that you don't change anything. I can also scale time by the strike price or the execution time. So now I'm going to have the execution time is tau is equal to 1. Right? And if I do that, then I have my sigma squared in the equation changes to sigma squared times t, and my r changes to r times t, right? Right, and then I'm also going to scale u to u divided by k, right? And if I do that, I end up with the following problem. Right, I'm going to have, okay, I'm going to go back to t instead of tau. Remember, that's what applied mathematicians do. They introduce some funky notation and then go, yeah, but even after scaling, I want to call time t, and so I'm just gonna do that. But this is the scaled problem, right? I'm going from time 0 to 1. Well, actually, I'm going the other way, right? Remember, now I'm going backwards in time, and it'll be a well-posed problem, right? I know what a u is here. With the scaling I took, this is just the maximum of s minus 1 and 0. So s is equal to 1 is going to be interesting, right? I've got u is equal to 0 here on that boundary, right? That's the company went bankrupt, so there's no call win there. It's valueless. Now, what's missing is a far field condition. And here is where I can look back at this equation and go, well, this is not something where I really understand everything about this equation with Math400 ideas, right? It's linear, okay, right? So that's good, right? It's variable coefficient, right? I've seen these kind of pieces of these problems, but not ones where the coefficients vary, right? Right. Well, okay, we did some variable coefficient work as long as the coefficients didn't vary too much. We could use some asymptotic analysis, and we could do some specific problems. But the interesting thing about those coefficients is that they're not bounded coefficients, right? They're coefficients, even though all of the signs are nice, right? Those coefficients are unbounded in S, right? So my initial conditions are unbounded in S. So this is something where the far field condition now is something I guess you have to take a little bit more seriously. We can't expect this solution to be bounded as S goes to 0 or as S goes to infinity, because the initial conditions aren't bounded as S goes to infinity. And the coefficients are getting bigger and bigger as S goes to infinity. So you have to be a little bit careful here. So this is the far field condition is the condition as S goes to infinity. Okay, so I can say in the literature that I looked at, where I'm not using analytic tricks. I wrote a little computational code, which I'll show you time permitting, right? I took something that I think is sensible. So I took that the derivative of value with stock price is 1, okay? And so you can make analytic progress on this problem. It's described on the Wikipedia page if you really want to look at it, and it involves the Green's function for the Cauchy problem for the heat equation. So hey, that would be like seeing an old friend, right? As you look through that, it's a sequence of transformations you have to do. And then you can get analytic expressions for how to value this asset at time 0. I like the idea of making a numerical approximation. So let me show you that in the 7 minutes remaining. And the MATLAB code I posted. This is partly in response to, I think, more than one student who said they were interested in seeing some numerical implementations of these types of problems. So yes, there's a sort of complicated series of transformations. You can get analytic solutions, which math finance people really like. But I'm happy to compute. Okay, so now I have to do some things here. So now it's this problem I'm computing, and now I have to stop sharing. Oh. Okay, how can I tell other Brian to stop sharing? Can I just make him stop sharing?
If you're both hosts, you can kick them off.
Can I?
You should be able to if you're both hosts.
Oh, okay, here we go. Make host. Ask to start video. Oh, bugger. No. Okay, so now it looks like I've got to meeting controls. Okay, here we go. Okay, what if I just killed that? Oh. Now you're seeing my screen. Okay, I hope I don't have anything embarrassing there, or at least not too embarrassing.
If you click on Zoom, there should be a little stop sharing button on the Zoom on your tablet.
Yeah, I understand there should be. Okay, oh, here we go. Here we go. Oh, yeah, new share. How about stop sharing? Okay, good. Okay. Sorry about that. I've never asked other Brian to stop sharing before. Okay, so now I'm going to share. I'll share my desktop. I don't think there's anything too bad here. Okay, and I've got this MATLAB code. Are you seeing it? Okay, so this is not a quality code. Okay, I don't know how much you know. This is this is just a finite difference code built on cell-centered differences in S. Remember, my domain is S going from 0 to infinity. Time is going to go from 0 to 1 because I've changed from t to 1 minus t. Okay, so that I'm doing the usual heat equation forward with all the terms having a changed sign. So I've got n grid points in a domain that goes out to s equals 2, where I implement the far field boundary condition. Now, 2 doesn't really seem like it's close to infinity, does it? Okay, okay, but okay, we'll see how to get around that. And the time stepping I'm using is I'm not sure how to say this politely, but simplistic time stepping. It's just forward Euler time stepping. And so there's all kinds of ways that this could be improved, but this is a code I threw together in a few minutes over the weekend to be able to show you. Okay, so I'll run it, right? And so here you're seeing the initial conditions, right? These are the conditions at time 1, right? That's that blue line. That's the maximum of S minus 1 and 0, right? That's the value at the end. And the red line is the value that the option has. Remember, in this, at time 0, remember, in this picture, the strike price is 1, right? And so typically you don't make a call option for the strike price lower than the initial price. So you're thinking of S at time 0. This is a known quantity, right? You're thinking of S at time 0 being less than 1. So let's look at S is equal 0.2 on the red line, right? Well, it looks like the value of the option to buy the stock at time 1 at value 1 is extremely low, right? And that's because if the stock price started at 0.2 with the variability that I put in, right, then it's so unlikely that it would ever reach 1 and give you a profit that the price is low, right? But now if you look, if the stock was at value 0.8, right? Well, then there is actually some significant value to be able to buy the stock potentially, right? At time 1 at the price 1, because the variability is big enough, it really could, get past 1, and then this asset would be worth something. Okay. Just as a couple of things, remember I put in this far field condition that I wasn't exactly sure of, right? And I'm doing this computation on my far field at S equals 2 instead of infinity. So one of the things I did was to say, well, let's keep the same discretization level, but take the far field condition out to time 4, right? And these are all plotted on the same thing, and you can see I don't change the solution at all by doing that, right? Now, that doesn't make my far field condition right? But at least it shows that it's consistent as I implement it farther and farther out to the left. I'm getting some consistent solutions. And of course, the other thing I did was to say, let me increase the grid resolution, right? And you can say the initial conditions change a little bit just because the S minus 1 bigger than or equal to 0 has an extra grid point in it, but the resulting solution is also right on top of the other one. So again, this is something which is more of a numerical discussion, but remember, that's my thing. These are the kind of things you can do to check that your computation is giving you some sort of reasonable approximation of what you say you're computing. Now, again, you can look in the literature and see different types of far field conditions, many of which they say are equivalent and that they give the same solution. So you can try those out in this format and see that they really are giving the right kind of results. Now I've gone over by a couple of minutes where I usually go. And so let me stop here and I'll stop recording the official lecture, but I'm happy to stay on.